what we were going to do today is just briefly go over the last slides for the 2D-NMR, and they're just kind of some examples, and actually they're much more relevant if Dr. Chang's group was in here. But we'll take a look at those because they're kind of an application of everything we've been doing. And then we're going to go into this, the chapter on other nuclei. So other, actually spin 1/2 nuclei we'll look at. All right. And so remember, well, you guys were here and we decided this, but Chad doesn't know this, I think, yet, but at least we haven't more time. It's not just next Tuesday.
That's right.
Week from Tuesday. Yep. But the exam will be through the 2D-NMR.
What about mass?
Huh?
What about mass?
Yeah, everything before 2D-NMR.
Yeah.
Mm-hmm.
So
No other nuclei.
Okay.
Yeah. Or the stereochemistry stuff that we're going to start talking about on Wednesday and Friday next week. All right, so this is from the text, but there's just a series of spectra for this lactose, which is a disaccharide. And I think the complexity of this, well, for one thing, we can look at just for the normal proton NMR or even C13 for a sugar. We have all of these protons. Almost every proton is on a carbon that has at least one oxygen, right? And so we end up with a big pile of H's that are all very overlapping and makes it very complicated. And this is just a disaccharide. What also makes this complicated is that this is a mixture of two different anomers, we'd call it. So notice in these two structures, they're both called beta lactose, or they're all called lactose. They have this is a galactose, I think, here, and this is a glucose here that are hooked together. They both have, this is the anomeric position where they're connected together, and these are both, if the oxygen is going up, this is called a beta anomer. Okay? So they're both the same in that, but at the other anomeric position, over here, because the anomeric positions, if there's not an ether, so these are both the functionality, it's the anomeric position, but this is called a hemiacetal, which can be in equilibrium between an alcohol and an aldehyde. Okay? And so because of that, they can open and close. You end up with a mixture of, this is the beta anomeric position here, and this one has the alcohol going down, and so this is the alpha. Okay? So it's actually a mixture of two compounds. All right? And so we can see that in the NMR. The anomeric positions are the most downfield because those positions have two oxygens attached, right? And so we have the alpha anomeric position, which has the alcohol axial and the hydrogen equatorial. And so this position only has the coupling from that proton to the adjacent position is at a 60-degree angle, right? Because it's equatorial to axial. And so this one has this small coupling constant, whereas the beta anomer here has the hydrogen being axial, and so it has this diaxial coupling. And so that has a larger J here. So beta, alpha 1 and beta 1. Okay? At the galactose position here, both of these, because they have the same stereochemistry, it just gives one signal. Even though there is this difference, but it's far enough away that this difference in stereochemistry at these anomeric positions doesn't affect the chemical shifts clear over here. Okay? So we essentially have, 3 signals here in the anomeric positions from these 2 compounds. Okay, we can also see the 3 anomeric positions here. And I think it's probably these 2, which is the ratio. It's like a 2-to-1 ratio of the what is it, beta to alpha. And some of these other ones we can see the split too, like there, probably there. We can see that these are the mixtures.
What is G1 in the upper one?
G1 is this proton here.
It's the same for all of them.
Yeah, so those are both the same. That's what I was saying, because it's far enough away from the
Affected by those ones.
Yeah. All right, so part of the challenge here is to try to have some technique so we can separate these enough to be able to see what's going on. So that was alpha. All right, so here's the normal cozy. I think this is the double quantum filtered cozy. And so, those are kind of blurry. I think you can start, say, with an anomeric position, and you can, go into this mix in here, and I'm not going to necessarily walk us through here. So which one was here? Let me look back. 1, for example. This is alpha 1. Oh, it says over here. Alpha 1 goes into, here's alpha 2, right in there. But yeah, it's got to, walk its way around. And so I think if you blew it up and you did it real carefully, you might be able to make your way through some of that. But obviously it's like, look at in here. This is really overlapped right in there. Okay, here's the HMQC, right? And so this would help us, I think, in our assignments of the cozy even, because we can see these, the CH2 group there. I think this is another CH2 group here. There's only 2 CH2 groups in the molecule on these 6 positions. And I think that in both cases, I think they're together. They just have one set of signals. But, this could help us, separate things. Here's the 3 anomeric carbons. I guess we won't take too long here. Here's the HMBC. So this is the long range coupling, and I'm not exactly sure if this has some kind of phase sensitive thing because all of these are like slanted like this, and I'm not exactly sure what the reason for that is. The one position that they've drawn out here, this one right here, is going from this G1. So here's G1, and it's going to probably both of these, beta 4 and alpha 4. So if we count both alpha and beta, 1, 2, 3, 4, this is the coupling from here over to here. So it's a 3-bond
Oh,
coupling. And in the HMBC, this is what's good. The other systems are all, we have these 2 spin systems, but connecting the 2 sugars, we don't have a proton spin system that bridges that. So the HMBC is the good place to go to try to bridge over a heteroatom like this. Okay, so this shows that the G1 is connected to this C4, and it shows it in both, right? I guess this bridges both of these 2. All right, so that's probably the most important one here. Now, ways to separate or to try to spread out these proton shifts are things like the TOXI. Remember the total correlation spectroscopy, and if we have the mixing time that's long enough, remember that the proton gets, there's essentially a coupling at the beginning, and then it gets relayed along the spin system. So the longer we have the mixing time, the longer that signal will get relayed, and we can essentially do it such that we can see the whole spin system. So if we start with this, I think this was the alpha 1, and if we go up here, this is long enough that we see connections to alpha 2, alpha 3, alpha 4, alpha 5, and alpha 6. So we see the whole spin system right here. Right, and we should have a similar thing here. So this would be, here's beta, this is beta 1. And so this would be the whole, so this is the alpha. So this is for the alpha anomer that I did first. This is for the beta anomer. So we can see, like, for example, this triplet that's the most upfield out of these, this is part of the beta spin system. And then here's the glucose or the galactose one, and we see all of the spins in that system. So we could take, like cuts out of this as well. We could draw a spectrum that is just along here. It would be like the projection, though, but we'd see where all those signals are in that whole mixture. The other way to do it for each of these two-dimensional experiments, like the TOXI, there's also one-dimensional experiments that you can do as well. So this is an example of that, where here we have on this bottom one, so in these cases, it's like the difference NOE where we irradiate on one signal, and then what we see is all of the signals that have been changed or that are relayed to from that signal. So in all of these bottom ones, they irradiated the beta 1 signal. And the good thing here, too, is these anomeric protons are all well resolved from one another. And this is showing what they do as they increase the mixing time. So here's this is just the standard or the regular spectrum at the bottom. So from beta 1 at 20 milliseconds, we just see the beta 2 protons. If we increase it to 40 milliseconds, we see the beta 2 and the beta 3 protons start showing up. We go to 80 milliseconds. We have the B4 here and the B5 protons start to show. And if we go up to 400 milliseconds, we see, so here's beta 5, and here's the 2 beta 6 protons. So in fact, now we're seeing actually the signals with their splitting and everything, and we can see, where they're showing up here. So beta 6, it's a little harder to see this other beta 6. Might be these two. And then, you can better pick them out from in there. At the top here's the same. So 400 millisecond mixing time was where they saw all of the signals. Here's irradiating alpha 1 with a 400 millisecond mixing time. And again, they see alpha 2, alpha 3, alpha 4, alpha 5, and the alpha 6 protons. So we're essentially extracting the signals from one spin system out of this mixture of essentially 3 compounds, or 3 spin systems. And here's the one for irradiating G1, so that's here, with a 400 millisecond. It doesn't seem like it goes quite as far on this one, though. G1 to G2, G3, G4, and G5 is just coming in, and it doesn't show the G6 yet. But it's a way again, to pull essentially one-dimensional spectra of individual spin systems. So here's another. There's all kinds of combinations of different experiments as well. So this one is called an HMQC Toxi experiment. Okay, so remember the HMQC is showing a 1-bond carbon-proton coupling. But then from the proton, the signal can be relayed along the spin system, so we can see from a carbon to all the protons in the spin system. Or, I guess, from the proton to even to all the carbons in the spin system. So, for example, we could look at this in 2 different ways here. Let's see. So here is, for example, here's the beta 1. So here, we'd probably start down here. Here's the beta 1 carbon. And if we go vertically, we can see all of the carbons attached to that proton. Okay, so in this case, we're going in red for beta 1. That's this one. We're going from essentially this proton to all of the carbons around the spin system. If we go the other direction, then essentially what we're doing is going from that carbon to all of the protons. Right? So if we go across here, right, we're going from a carbon to the protons. We're seeing all of the protons. And in this direction over here, we are going from the proton, from the proton to all the carbons. Right, and we can see that from each one. So if we look at, say if we go to, I guess they should be showing similar things. So if that's beta 1, if we go, and this is showing in the green down there all of the positions in that spin system, then we should be able to go to another signal. So here's beta 2, and if the mixing time is long enough, it should essentially show all of the same protons in that system. or the same carbons that going in the other. So here's beta 2 here, and if we go this direction, we're seeing all the same ones as we saw over here. Right, so it's really able to pull apart, and you look at some of these, and there's even though there's a ton of overlap in the proton NMR, there's not so much in the two-dimensional spectrum.
That's so cool. I mean, like, in my stuff, I don't think I could ever.
Find an application, right.
But it's really cool.
Right,
Yeah.
right.
Yeah.
All right, so what's this? Oh, this last one is a, remember we talked about that there was two different kinds of NOE, two-dimensional NOE experiments. And this one, I don't know what the molecular weights are here, but they did the ROSY in this case, which is better. We talked about especially for compounds that are in kind of that 1,000 molecular weight kind of range. And so in this case, so we have the different protons. So let's see, for alpha 1 here, it essentially doesn't show anything, except this is alpha 1 to alpha 2. This, I guess what you can see is you can actually see a cozy. So this alpha 1 to alpha 2 isn't really an NOE, but it's a J or scalar coupling. All right? And the reason is because this is equatorial, it's not close to any of the other protons, and it just shows the coupling to here. If, alternatively, like beta 1 here, if this proton is axial, then we can see NOEs to the other two axial protons.
How far it can go for the NME?
Well,
just 2 bonds, 3 bonds, something like that.
yeah, well, no, it's not really a matter of the number of bonds, because you can have molecules like, DNA, it's proximity.
Space.
I don't remember exactly like how many angstroms away or something it has to be, but the relationship drops off to like the distance to the 6th power or something like that. So it drops off very rapidly.
So it's somewhere. What's that? Like, never mind. Don't worry about it. Magnets, like that magnetic decay.
Oh,
is that because they have it? I forgot the formula for it.
Okay.
It's no. I'll be. Yep. Ignore me.
Okay. All right. So you can do these 1,3 diaxial interactions, though. But, like in proteins or in DNA or something where they have these helices and things like this, they can see NOEs, along the helix, right? Which would be actually quite a few bonds away and things like that. But it's good for these 1,3 diaxial positions as well. So for beta 1, they see some to, should be beta 3. So this is beta 3. And to beta 5, which would be the other axial position. Right? And then they see the cozy, the coupling to beta 2. So this is kind of it seems like you can run this, if I'm remembering back. I don't know if they said it here, but if this is kind of a phase-sensitive one, I think the cozy couplings can be either one direction and the NOEs the other direction, or one will be show phase information and the other one doesn't, or something. I think there is a way that you can see the difference. And then for the galactose, so G1, so here's G1, which is the same in both. this should also show,
NOE for
yeah, so let's see what else do they show. This one seems to be showing.
Does it flip in the space and have more NOE with other proton as well, or not?
What?
Or, for example, it flips from the anomeric carbon to the oxygen, and then have NOE with other.
If it's ring flipping or something like that, I think it can, but in this case, I think there'd be one conformation that's more favorable.
And
If it's
just
flipping,
fixing that one.
I think the amount of NOE would be proportional to the population or how much time it spends
Okay.
in.
In which stereo.
Right, so if you did have some group that was rotating and you had two protons on each side, it might see some NOE to one side and some to the other side.
I found an answer.
Uh-huh.
It's rough. Max roughly is about four angstroms.
Okay.
NOE.
Okay.
So, I mean that makes sense.
Yeah, I was thinking maybe 5 or something, but yeah, so 4, that's about the same range. And I don't know for these like 1,3 diaxial interactions what the different distance is there. So here's the main one. So here was the cozy interaction to G2 and G3 and G5. I'm not sure why they're seeing.
What is the number of the G2, G3, and G5 and the structure?
Well, in each of the sugars, they always start with 1 at the anomeric
Okay.
position, and then they number, up the chain, right? Because remember, all these sugars, if you had just monomers, they would have an open chain form and the cyclic form. I'm not sure, because G1 is kind of showing so much other stuff here, if it's actually able to show, for example, well, those
Beta
are
6 prime, for example, beta 6.
beta 6. Yeah, I don't know if it can go, because that would be from here
Oh, to the other.
to here, to this position.
It may be.
It
close
may
enough.
be, if that thing is rotating, yeah, possibly. Or from, let's see, I was looking for the alpha and beta 4, and here they're right here, but they're also buried underneath G3, so that's kind of hard to see. But yeah, beta 6, alpha 5. Yeah, I'm not quite sure. Those seem a little farther away than I might expect, but yeah. All right, so this was just kind of an example of applications of some of the techniques we've looked at to something that's a little bit more complicated. There's also some examples in the book. There was one, of like a tripeptide or something, and, something like that. Also, where you have amino acids, and just like this, you have these isolated spin systems, right? And so that's a good place to use like the toxy, or maybe even this HMQC toxy or something, that you end up seeing the whole spin systems isolated from one another. All right, so that's the end, really, of our 2D-NMR. All right, so let me